So, brief content overview. The following questions require students to apply the concepts of evaluating two-way tables of relative frequencies to calculate joint, marginal, and conditional probabilities, recognize if two events are independent in contextual situations, and compute probabilities for binomial distributions. So in terms of concepts, two-way tables of relative frequencies describes the relationships between two variables or categories. So in this case, it displays the relationship of data between the type of gender of a respondent and their type of response. The total sum of the relative frequencies of a table should always equate 1. Independence in events describes when one event's outcome doesn't affect the other's probability. For example, the outcome of a first roll of a dice doesn't affect the second rolls. And finally, a binomial distribution has specific requirements such that the events involved have binary outcomes, are independent, have a set number of trials, and exhibit the same probability for each trial. And this is known as the Bin's requirements.
A medical researcher surveyed a large group of men and women about whether they take medicine as prescribed. The responses were categorized as never, sometimes, or always. The relative frequency of each category is shown in the table. Part A, Question 1. What is the probability that the person selected will be someone whose response is never and who is a woman? To answer this problem, you first need to look at the table. The question tells us that we are looking for women that were surveyed and also said they never take their medicine. If we look at the table and follow the events of identifying as a woman and responding with never, these events intersect at 0.636, which is the answer to this probability question. Question 2. What is the probability that the person selected will be someone whose response is never or who is a woman? We can solve this problem by using the equation probability of responding never plus the probability of surveying a woman minus probability of responding never and being a woman. Looking back at the table, the probability of responding never is found to be 0.12, and the probability of surveying a woman comes out to 0.53. When we add 0.12 and 0.53, they equal 0.65. However, we cannot just add these two together, we must also subtract by the probability of responding never and being a woman, which is 0.636. We subtract to cancel out the overlap that occurs between the two events. Once we subtract 0.636 from 0.65, our final answer of someone whose response is never or who is a woman equals 0.5864. Question 3. What is the probability that the person selected will be someone whose response is never, given that the person is a woman? The probability that the person selected will respond with never, given that they are a woman, can be simplified to the equation probability that they responded with never and also identify as a woman, divided by the probability the person selected is a woman. We know that the probability of responding never and being a woman is 0.0636 from the first question. And looking at the table, the probability the person selected is a woman is 0.53. To get the answer, simply divide 0.0636 by 0.53 to get 0.12, which is the probability of someone whose response is never, given that the person is a woman.
The scoring for Part A is relatively simple. It's graded mostly on accuracy. It's as follows. If you get all 4 correct, you get an E. If you get only 1 or 2, then you get a P, and if none of the probabilities are correct, you get an I. So make sure to do them accurately. As far as alternative solutions go, there wasn't really much wiggle room here. However, one of the possible alternative solutions for Part 2 may be the total summation of the probabilities of being a woman and responding never without the repetition of the value 0.0636. This achieves the same solution and is thus accepted via scoring guides. And now, on to Part B. So, the question for Part B is, for the people surveyed, are the events of being a person whose response is never and being a woman independent? And then it asks you to justify your answer. The way to solve this question is pretty simple. The probability of someone never taking the correct dose of medicine as prescribed, 0.12, is equivalent to the probability that specifically a woman never takes the correct dose of medicine as prescribed, also 0.12. If you are paying attention, which I hope you are, you might have noticed that these two values are not, in fact, both 0.12. However, you do have to account for the total that it's out of. What I'm saying is that the total of never taking your medicine is out of 1.00. However, the total for women is only 0.53. So, if you were to do 0.0636 over 0.53, that would be equal to 0.12, and that is where both values being 0.12 is coming from. If we say that n is equal to the probability someone never takes the correct dose, and w equals whether or not they are a woman or not, then the situation can be modeled with the following. Probability of n equals 0.12 equals p n given w, which is also equal to 0.12. Seeing that these two probabilities are equal, then independence can be established, as knowing either variable gives no insight into the other. The chances of someone never taking the correct dose does not increase or decrease when whether or not they are a woman is specified and known to the audience. As far as scoring guidelines go, the main thing is that numerical values are required to be integrated into the justification of a student's answer. If numbers are missing in a solution, points are marked off. For instance, if a student simply stated the events are independent and gave a worded explanation without actual calculations, the highest score they would receive would be a P. Additional sample solution errors include if a student made calculation errors, which would also, again, earn them a P. And yes, I am indeed sitting on the ground right now, not squatting, if my terrible drawing made you think that, because I recorded this in the middle of editing, which I have been doing for the past 3 hours, and I still have about 1.5 more hours to go. So, buckle up.
Part C. Assume that in a large population, the probability that a person will always take medicine as prescribed is 0.54. If 5 people are selected at random from the population, what is the probability that at least 4 of the people selected will always take medicine as prescribed? So first, let's confirm if the situation follows a binomial distribution. Looking at the binary outcomes, it can be established that taking the medicine as prescribed is considered the success of the situation, and doing the opposite is the failure. So the events are also independent, as one's choice in taking medicine doesn't affect the outcome of another. The number of trials are also a set number, since 5 people are being selected as a sample. And finally, the same probability is seen for each trial, being that the probability for a person taking the medicine as prescribed is 0.54, and this value stays constant. So looking at all of these confirms the BINS or BINS requirements. Now, confirming these conditions, we note that the situation given follows a binomial distribution and can apply its corresponding formula. Since we need to find the probability that at least 4 people out of the 5 will always take the medicine as prescribed, we must find the probability that 4 people will take the medicine as prescribed and 5 people will take the medicine as prescribed, which is the maximum. Then we would add these probabilities together. So using the binomial probability formula, we get around 0.195 for probability of x equals 4, or P of x equals 4, and 0.046 for probability of x equals 5. Adding these up, we get a probability of around 0.241 for P of x is greater than or equal to 4. In terms of additional sample answers, students may skip the step of proving that the situation given follows a binomial distribution and instead go straight ahead with the formula. It is important to not make this mistake, as the scoring guidelines specifically look for the clear indication that the situation given is a binomial distribution. So for instance, if students were to simply write the formula without stating the number of trials or the probability value, they would be penalized. Other scoring requirements include the correct boundary condition, aka at least 4 people, and the correct value. So an example of a solution that would be deemed incorrect would be if the student solved for the probability of only 4 people and not both 4 and 5 people taking the medicine as prescribed. It is essential that students understand the meaning of the phrase at least 4 people and understand that it requires a summation of probabilities.
Well, that's it. That's our stats project. 8 minutes and 57-ish seconds of hopefully entertaining lecturing. I hope you all enjoyed. What follows is the credits, which you don't need to watch except for, knowing who did what and everything. Hope you all have a good rest of your day and all that, and I wish you luck on your FRQ and your final. Yeah.